Greetings, in this one we'll be talking about the statement and proving it that every tree has a leaf. So I'll write it. Every tree has a leaf. In the context of graph theory, of course, where trees are acyclic connected graphs, and leaf is a special vertex in a tree that has a degree of 1, so it's connected by one edge to the tree, but not in the middle between two edges. So it doesn't have a degree of being connected by edges to more than one vertex. So that's a leaf. So you have a graph, and now it looks like it's cyclic. It's not. It's a tree, just a picture. And I'll call the graph G. So the acyclic tree graph that I have here we'll call G. And then there's something like a leaf going out, and that leaf is that vertex that's connected by only one edge to the graph. So that vertex has degree 1, then it's a leaf. And the statement is every tree has a leaf. So we don't have to draw this in this way. I mean, the leaf would be here. We could name the vertex anything. For example, X, and say X is a leaf, as long as it's connected by only one edge to the rest of the graph here. But let's prove the statement itself. And for it we'll use an argument involving longest possible path. So there is this take a path P on the tree. So tree, let's say we have a tree graph G on G, and P is G's longest path, is longest path that one can find in the graph G. That's a tree, and we can denote it as like a line, like here. And then what we can also think about is, well, the endpoint we can take an endpoint A, for example. Let's call it A, lowercase a, like this. And we see A should be a leaf because that's the longest path, and it's at the end of the path. And we see, alright, so it should be connected to one edge here, should be a leaf. And now let's prove that it really is a leaf, that cannot be something different. And we'll do that by contradicting the assumption that it's not true that it's a leaf. So assume that A is not a leaf. So this is an end of it here. Right, so there can be more vertices on the way, like this. But assume A, vertex A, in the vertex set of the graph is not a leaf. So its degree is not 1. And then we have two options that we can consider. First of all, if it's not a leaf, it will lead to one thing. It will mean that it doesn't end like this, but there's some other edge, and that edge is either leading to yet another vertex, and we'll call that a vertex B. So if we suppose that A is not a leaf, this vertex A is not a leaf, that means from it to the other side, from the longest path, must be something more, so the degree is higher than 1. And it goes to some other vertex B, and that B is either outside of the path itself or it's on the path. I mean, of course, it's not at both of the places, but I draw it in the same picture like this. So first option is it's outside the path itself that we were considering. Second option is here. So in such case, it would be going back to some point on the path. I'm not saying it's the one right before in the chain, before A, it could be anything. Alright, so I can draw more vertices possibly. We don't consider concrete amount, it's abstract. But assume that A is not a leaf, then there's got to be some edge connected to A from the other side, connected to another. So then assume then there exists an edge. There exists an edge AB, and that edge has two options. Now here are the two options we have. The first option is either this is our path B, right? So path B is this whole picture, just to make sure we remind ourselves of that fact, this whole thing. And the first option is that this vertex B, thanks to which we have that other extra edge possibility, before we prove that it's not possible, but is either in the vertex set of the path, it's on the path, or it's not on the path. And now we prove that both of these options are not possible. So it's on the path, then we get a cycle involving AB. Right? So there exists a cycle with the path, but that's not possible because it should be, there cannot be a cycle because we're considering a tree. So that's no, because a tree has no cycles, right? Let's not forget the graph we're considering here the whole time should be a tree. We're talking about a tree. We're saying that every tree has a leaf, so we're talking about trees. Second option is that vertex B is not on the path itself considered, and that means that the path, if we add the vertex B, is the longest path, but that doesn't work as well because P was the longest path, alright? So that's also in contradiction. So it doesn't work if B is on the path or if it's not on the path. Both things don't work. So we contradicted the assumption that this A here is not a leaf, so it must be a leaf. Alright, so with these few logical steps, we've proven this statement that every tree has a leaf.